Last time we dealt with force, and we defined force to be a push or a pull that can change the motion of an object. And when we did the equilibrium activities, we discovered that if an object is not changing its motion, if it's at rest and it's staying at rest, that the forces that were acting on it added up to zero. That's what we observed. Today we're going to formalize these ideas with Newton's first law, and then we're going to develop Newton's second law, and we're going to create an equation that we can use to solve lots of very, very important kinds of problems. So let's talk about Newton's first law. It's called the law of inertia. If you have an object that's at rest, let's just say you put a box in the middle of the floor, it's just going to stay there. Now there are forces acting on it, right? Gravity's pulling it down and the floor is pushing up on it, but as we saw in the last assignment, these forces cancel each other out. Or when you add them together, you get zero. And so, so there's no leftover force to change the motion of this object. And it just stays at rest. If it's at rest, it will stay at rest. Most of the objects you look around that are laying down on the table are staying at rest. Well, there are forces acting on them, but if you were to add up all those forces, you would get zero force, zero net force. Now, imagine you're in space. You got a spacesuit on, and you're holding a baseball, and you're far away from the influence of the gravity of the Earth or the sun or anything else, and you throw that ball. So here's the baseball, and it's moving through space. Well, guess what it's going to do? Now, if I took a baseball and threw it in this room, it would hit the floor, it hit a wall, hit a chair, or whatever, and it would rub against things and make noise, and eventually it would come to rest. But if you can use your imagination, imagine you're way out in space and you throw this ball. There's nothing for it to hit. There's nothing that's going to change the direction of its motion. It's just going to keep going and going and going forever. There's nothing to change its motion. Now, if you're close to the sun or whatever, the sun's gravity will make it go into a circle, or Earth's gravity, whatever. But if you imagine you're away from everything, and you just throw that ball in your imagination, there's nothing that will change the motion of that ball. So objects in motion will stay in motion with constant velocity, constant speed, constant direction forever. Now the way I like to put that is, things don't change the way they are moving unless you force them to. Things don't change what they're doing unless you force them to do it, unless there's some kind of force on it that will change its motion. This is much easier for us to imagine because we're used to thinking of things traveling through space. But a long time ago, people didn't even have that in their imaginations. It wasn't something that very many people anyway could even imagine. And they just said, look, you throw something, eventually everything comes to rest. So they thought that everything should come to rest, and that if you threw an object, it would essentially use up all its motion and come to rest. They have this idea called impetus. Well, we now realize that that was wrong. That what's happening when you throw something near the earth, that there's always something that will apply forces to it to make it stop moving eventually. But if there were no things applying forces to it, it would just keep going and going forever. Now let's talk about Newton's second law. This is the law of acceleration. And the law of acceleration, well, I'll demonstrate it here. Suppose here's a track, flat surface, and suppose you have a box with some stuff in it, and you pull on it with a certain amount of force. And this force is not being canceled out by anything. There's nothing pulling back on it. So what's this crate going to do? What's this little car going to do? It's going to accelerate. It's going to change. We're going to change its motion. And we call changing motion acceleration. If a force is not canceled out by anything, we're going to call this the net force. And the net force will cause this object to accelerate. Now, it's been empirically observed, that is, we've done lots of experiments, and we've shown that for this object, if I make the force twice as big, I'm going to get twice the acceleration. If I make the net force 10 times bigger, I'm going to get 10 times the acceleration. In other words, force and acceleration are directly proportional. But how much acceleration do I get? What does that depend on? Well, it turns out it depends on how much stuff I put in here. If I put in more stuff, it's harder and harder to accelerate. Does that make sense? The more stuff you put in here, the harder, if you just pull at the same force, you're not going to accelerate as fast. Doesn't that make sense? The more stuff, or if you want to make it accelerate at a constant rate, you have to push harder. The more mass it has, the more stuff it has, the more you have to push on it. And we call all this stuff, well, we call it mass or inertia. Mass is how we measure inertia. And the more mass something has, the harder it is to accelerate. In fact, that's one way we can define mass. We can define mass to be how much force, well, the ratio between force and acceleration. But we use the letter m to represent mass. And we measure mass with one of these. This thing right here. This big chunk of metal, brass I think, is 1 kilogram. How do we know? Because right there it says, I don't know if you can see it on the camera. There we go, 1 kilogram. Now they actually have a chunk of metal in France somewhere that is defined to be 1 kilogram. They're looking at a different way of defining the kilogram. I think they're in the process of defining the kilogram with an experimental procedure rather than a physical object. But 1 kilogram is a big hefty chunk of metal. Most of you have a mass of about 50, 60 kilograms. I have a mass of about 95 to 100 kilograms. Some of you are, we all have different masses, and kilogram. Now, in chemistry, you dealt with grams, but in physics, we usually measure mass with kilograms, and it's abbreviated with a kg, kilogram. And it turns out that if you do the experiment, you get F net equals ma. And I'll rewrite it here because that's, equals mass times acceleration. Now notice that force, we talked about this last time, force is a vector. It has magnitude and direction. Acceleration has magnitude and direction. And the direction of the net force will be the direction of the acceleration. Now this makes sense. If you push on something, it's going to change its motion in that direction. Okay? So mass determines how much acceleration you get. The more mass you have, the less acceleration you'll have, because for the same amount of net force. Now let's take a look at this in terms of units. We have mass is measured in kilograms. Acceleration is measured in meters per second every second, or meters per second squared. So we have a kilogram meter per second squared here. Well, we have a name for that combination of units. A kilogram meter per second squared. We don't want to write that every time we write down a force. So we've combined all those units into one unit, and we call it the Newton. So 1 Newton is 1 kilogram meter per second squared. That's the definition of a Newton. Now, last time we threw this thing around. This thing, when you hold it in your hand, it's pushing down on your hand with a force of 1 Newton. So a Newton isn't very much. And when you think about this 1 kilogram mass here, 1 Newton is the force I need to push on this thing to accelerate it at 1 meter per second squared, which is about like this. Let's see, it starts from rest, and we go. It's not very much force. It's not a lot of acceleration. Now, one thing about mass is that, we'll talk about mass versus weight next time, but, you can actually feel the difficulty in changing the motion of an object based on how much mass it has. If I take this and I shake it back and forth, oof, that's actually pretty hard to do. This thing, you can feel the difficulty in stopping it and making it go. Look at this cute little baby one. Aww. Okay. This is 100 grams or 0.1 kilograms, and I shake this thing, and it's much easier. Much easier to shake it back and forth. And now, look at that one. Oh, so tiny, 10 grams. I mean, I hardly even notice it. Moving this back and forth. I mean, I guess I can feel it a little bit, but, and by the way, that's how you feel mass. When I hold it like this, I'm feeling weight. And I don't really, and that's different than mass. We'll talk about why weight is different than mass later on. They are related. But when I do this, when I feel how hard it is to move it back and forth, that's when I'm experiencing mass. Very little mass, medium amount of mass, ugh, lots of mass. One way to think about it, if I was in space, floating around in space on the International Space Station, if I were to hold this in my hand like this, it wouldn't feel like anything. In fact, it would just slowly drift off my hand and float off. But if I were to grab it and then shake it, it would feel just like this. It would be hard to shake. Oh. Okay, so it doesn't matter what planet you're on, or if you're not in space, if you're in zero gravity environment, it would be just as difficult to move around, to change its motion around. Now finally, let's take a look at this idea of net force. Well, let's take a look at a really easy problem. Here's given. Suppose I have an object, it's just floating in space all by itself. And let's say it had a mass of 10 kilograms. So it's about 22 pounds. And I'm going to pull on it with the force of 30 newtons. And I'm going to say that's the net force. So there's no other forces acting on it, or there is canceling out. This is the net force acting on our object. And let's say initially it's at rest. Let's find the acceleration, and B, the final velocity at t equals 3 seconds. Let's do this problem. So again, I have an object at rest, it has a mass of 10 kilograms. I'm going to pull on it with a force of 30 newtons for 3 seconds. And I want to know, what is the final velocity? Well, we have this equation. The net force equals mass times acceleration. So the acceleration is just going to be the net force divided by the mass. And the net force was given to be 30 newtons divided by the mass, which is given to be 10 kilograms. Now watch the units here. 30 divided by 10 is 3. And a newton is a kilogram meter per second squared. I'm going to divide that by kilograms, and notice that the kilograms cancel. And so the acceleration will be 3 meters per second squared. Easy. And the direction of this acceleration will be 0 degrees or to the right, or however you want to express that. So that's part A. Now part B, well, now that I know the acceleration, because look, if the net force is constant, the acceleration will be constant, and that means I can use the kinematic equations. And if I want to know the final velocity, given time, acceleration, and initial velocity, I use the first kinematic equation. So we're still going to use those kinematic equations. They're given to be 3 seconds. 9 meters per second is my final velocity. So if I know the mass and I know the net force, I can now figure out the acceleration, and I can make predictions about the motion of the object. And that's a very powerful thing. You know, if I'm in that Tesla Model X and I hit the throttle and I know what my acceleration is, I know what the net force is, I know what the mass of the car is, you know, I can make all kinds of calculations. And believe me, the engineers and so on who designed and built the Tesla Model X, they knew how to use all these ideas to design that beautiful car. Let's work another problem. Call this example. Suppose I'm given this. I'm going to have the same 10 kilogram crate. I'm going to put it on wheels, and I'm going to have a 30 Newton force, but I'm going to call this F1, and I'm going to call this F2. And what do I want to find? I want to find the net force. And B, I want to find the acceleration. And we'll end there because we're running out of time. Well, what do I mean by the net force? I mean, can you look at this and just tell me what the net force is? In what, 20 newtons in what direction? To the right. Now, how did you get 20? Okay, 30 minus 10. But really what you did is you did vector addition, didn't you? You added these as vectors. You said 30 newtons to the right plus negative 10 newtons to the left, right? Or negative 10 newtons in the x direction. So really, to get the net force, what do you have to do? Now, everybody pay attention to this. I know it's just an example, but when I say net force, I mean to, have you ever seen that symbol before? Sum all the forces acting on the object. It's a summation sign. And that will equal the mass times the acceleration. This right here is the most important equation in physics, in that understanding this and how to use it enables us to do engineering. Before Newton, this is Newton's second law right here. This is Newton's second law. And before we understood this and how to use it, we couldn't do engineering. We did craftsmanship. We had tradesmen or tradespeople. But once we did this, we could actually create mathematical models, and we could understand how forces are acting within structures and how things will move under those forces. And thus we could design machines. So this simple little lovely equation gave us the technological world we live in today. I mean, it's kind of amazing to think about. This is why Newton is remembered today, because of this idea. So I will say, well, it's F1 plus F2. It's vector addition. So that's going to be 30 newtons in the x, 0 in the y. We don't even really need to worry about y. And negative 10 newtons in the x and 0 in the y gives us 20 newtons in the x. So that's my net force. And we just say it in the x direction. Now what's the acceleration? Well, we're going to take that net force and divide it by the mass, because F equals ma. And so we have what? Oops, I almost said the wrong thing. 20 newtons divided by 10 kilograms gives our answer A equals 2 meters per second squared It is that easy. But don't worry, because it's going to get a lot harder here pretty soon. So enjoy it while you can. That is all